Hello, my name is Henry McKinnon. I'm here today to present to you my work for Lab 1 Constant Velocity for Physics 2211, Section A. To introduce you to this lab, I will tell you about its purpose. The goal of this lab is to better understand Newton's second law by observing an object that has a constant speed and does not change direction. To do this, we will be using a position-first time graph created with an online program using the data to achieve this purpose. There will be a few assumptions for this lab. First of all, there will be no air resistance, no friction. Normal force will equal gravitational force. It will be done on a flat surface, and we are only observing on the x-axis, not the displacement on the y and z-axes. According to Newton's second law, an object at rest starts to move when a force acts on it. This force causes the object to accelerate in the same direction as the force. If no net force is acting on an object, then there will be no change in momentum and velocity will be constant. Force is one of the fundamental principles of any physical system. Significance of Newton's second law is that explains how to calculate this force. In our experiment, F net will equal 0 and velocity final will equal velocity initial. We know this to be true because F net times time is equal to the change of momentum. We can then change the change in momentum into PF minus PI. We then need to solve for the momentum final and to divide it by mass. Next, I'll talk about the experiment and the procedure. The first step we do is take a video of the rolling object. In this case, I used a water bottle. It will be rolling on a flat surface, which will be this is my desk. We then use the tracker software to determine the position versus time of the rolling object, the position first being at x equals 0. Next, we use GlowScript to create a computational model that uses Newton's second law to describe the observation in the video. We create a position versus time and compare the results of both of the models. The rolling water bottle will be the system, and the surroundings will be the friction, gravity, and the force applied to originally get the water bottle rolling. Like I said earlier, F net equals 0 and Vf will equal Vi. Here we have the observations of the water bottle rolling on the deck. As you can see, we use the tracker program. The initial position was at 0 meters or at 0x, and initial velocity was 0.156 meters a second, found by calculating using delta r over delta t. As you saw on the right, we use the software to get the position versus the time, and we will be using that later in the experiment. Here I have the GlowScript code that I used. A few things are left unchanged, like the system mass, the initial conditions, the position and velocity were all set at 0. Time obviously started at 0. Delta, as a video was filmed at 30 frames per second, we did 1 divided by 30 to get that number. So we had to find the right position and velocity numbers to use, and that was used during using the tracker software. I used the position and time to create the settings that would allow us to get an accurate graph of what it might look like. As you can see here, these are the results of both of the different models. As you can see, there's a little bit of a difference, most likely because of stuff like if friction happened or maybe the table wasn't perfectly smooth, stuff like that would affect the results. Flipping the axes, like changing the x values to negative, will make the slope negative. This would not have affected the results, though. The same conclusion could be drawn from the comparison made earlier. So the net force for this experiment is equal to 0. So we have to figure out, is it possible for you to say how many pushes and pulls are added together to get 0 negative force in the case that we observed? And I have to say no, it is not possible to tell how many pushes and pulls there are. There are so many different factors that go into it, so many different pushes and pulls that it's not possible to figure all of them out. And then for sources of error, of course, there are many possible cases. There's the classic human error with the programming or the programs that I created, and then obviously the surrounding forces. You can't control everything that goes on. There's just so many different factors that could have caused some kind of error.